Welcome to the Agrawal classes. Today we will solve some numerical problems in the tutorial class 3 in the thermodynamics series, where we are studying the thermodynamics for the engineering students. Let us consider the first question. A cyclic heat engine operates between a source temperature of 800 degrees centigrade and a sink temperature of 30 degrees centigrade. What is the least rate of heat rejection per kilowatt net output of the engine? In this question, it is given that a cyclic heat engine is operating between a temperature of 800 degrees centigrade and 30 degrees centigrade, and we have to find out the minimum amount of heat rejection for 1 kilowatt net output of the engine. So when we are talking of the least rate of heat rejection, at that time the efficiency must be maximum, and the efficiency will be maximum when we are considering a reversible heat engine. So here let us consider a reversible heat engine. When we are considering the reversible heat engine, then we can consider the Carnot cycle. So here we are taking a heat engine which is reversible and is operating between temperature T1 and T2. The temperature T1 is given as 800 degrees centigrade. Remember here, whenever we are applying the Carnot cycle, we are applying the temperatures in Kelvin, because this when we define the thermodynamic temperature scale, at that time the temperature was taken as in Kelvin, which is the minimum possible. The value of the Kelvin temperature is 0. So here we are considering this heat engine taking Q1 amount of heat and producing net amount of work done as Q1 minus Q2, and that is given as 1 kilowatt. And for that, how much heat is rejected? Q2 at temperature T2, that is 30 degrees centigrade, and is equivalent to 303 Kelvin. So for the maximum efficiency, we are considering the reversible cycle. And when we are considering the reversible cycle, the efficiency is given as 1 minus T2 upon T1. So substituting the values, we get the efficiency as 0.718. The efficiency can be written as W net upon Q1 is equals to efficiency. So we can find out the value of Q1, that is the heat supplied to the engine per kilowatt of output, assuming W net as 1 kilowatt. So we can calculate the Q1, that is coming out to be 1.37392 kilowatt. So from this heat engine, we can find out the Q2 as Q1 minus W is equals to Q2. So Q2 is equals to 1.392 minus 1, that is 0.392 kilowatt. And this amount of heat rejection will be minimum when we had considered this engine as a reversible heat engine. So for this question, you can have that the least rate of heat rejection will be 0.392 kilowatt. Again I'm saying, remember, whenever we are using the temperatures in the Carnot cycle, they are in Kelvin. Whatever is given in the question is in centigrade or Fahrenheit, or maybe in Kelvin, but you have to keep this into a Kelvin. Let us consider a second question. A domestic food freezer maintains a temperature of minus 15 degrees centigrade. The ambient air temperature is 30 degrees centigrade. If the heat leaks into the freezer at the continuous rate of 1.75 kilojoules per second, what is the least power necessary to pump this heat out continuously? So in this question, it is given a domestic food freezer is there, which is maintained at minus 15 degrees centigrade, and the atmospheric temperature is 30 degrees centigrade. Because the freezer temperature is lower than the atmospheric temperature, so the heat is leaking into the freezer, because the heat flows from high temperature to low temperature. Although the freezer is insulated, but it is not perfectly insulated, so continuously some amount of heat is leaking into the freezer, and that amount is given as 1.75 kilojoules per second. So if we want to the freezer to be at minus 15 degrees centigrade only, then we have to remove this Q2 amount of heat, 1.75 kilojoules, which is leaking inside the freezer that you have to take out from the freezer continuously. So for this we have to put a refrigeration system. So here we are putting a refrigeration system which is taking Q2 amount of heat from this freezer, so that the amount entering in and amount going out is same. So the freezer temperature will remain same, minus 15 degrees centigrade. So as it is a refrigerator, it is taking some heat from a lower temperature. It cannot transfer it to a higher temperature unless we do some work on it. So say W amount of work we are doing on the refrigerator. So it is converting this heat of a lower temperature to a higher temperature and is discharging it to the ambient at higher temperature, that is 30 degrees centigrade. So here the T2 is given as minus 15 degrees centigrade. So as I said, whenever we are using the Carnot cycle, our refrigeration system or the heat pump, we had to take the temperature in Kelvin. So minus 15 plus 273, 258 Kelvin, and ambient temperature 30 degrees centigrade, that is 30 plus 270, 303 Kelvin. When it is required that the least power necessary to pump this heat out, that means we have to consider the most efficient refrigeration system. So when we are considering the most efficient refrigeration system, then it is a reversible heat engine. So the reversible heat engine, or in the heat engine, we have a relation that Q1 upon T1 is equals to Q2 upon T2. So we can calculate Q1 as T1 into Q2 upon T2. Substituting the value, we get the value of Q1, that is 2.06 kilojoules per second, is rejected by this refrigeration system to an ambient temperature. If we apply the first law of thermodynamics, then the W is equals to Q1 minus Q2, that is 2.06 minus 1.75, so it comes out to be 0.3 kilojoules per second. As it is a watt, so we can write it in a kilowatt term, watt term or kilowatt term. So it is 0.31 kilowatt. That means here we need a pump which is operating at 0.31 kilowatt. So this refrigeration system will be maintained at minus 15 degrees centigrade, as it is taking out the 1.75 kilojoules per second, the heat from the freezer. Now let us consider a third question for this tutorial. A reversible heat engine in a satellite operates between hot reservoir at T1 and a radiating panel at T2. Radiation from the panel is proportional to its area and T2 to the power 4 for a given work output and value of T1. Show that the area of the panel will be minimum when T2 upon T1 is equals to 0.75. Then determine the maximum area of the panel for an output of 1 kilowatt if the constant of proportionality is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4, and T1 is 1000 Kelvin. So in this particular question, it is given in a satellite a heat engine is operating and between a temperature T1 and T2, and the amount of heat rejected by this heat engine is transferred to a panel, and this panel is ultimately radiating the heat into the atmosphere. And we have to prove that T2 upon T1 is equals to 0.75 when the area is minimum. And then finally we had to find out the maximum area of the panel for 1 kilowatt of output from the engine. So here we are considering a heat engine which is on the satellite and is taking the heat and is taking the heat Q1 at temperature T1 from the satellite and producing W amount of work and rejecting Q2 amount of heat to the panel at temperature T2. and this panel is radiating the heat to the surrounding, to the atmosphere, as Q2 is equals to QA T to the power 4. So let us consider that area of this panel is A and the temperature is given as T2. So the amount of heat radiating by this panel will be equals to Q2 and is proportional to the area, and T2 to the power 4 as it is given, proportional to the area and T to the power 4. So we can say that the Q is equals to K A T to the power 4 if we put the K as the proportionality constant. So this is the amount of heat radiated by the panel, and that is the same amount is heat rejected by this heat engine. So the efficiency of the heat engine we know as W upon Q, and if we are considering this as a reversible engine as it is given, so it will be equals to T1 minus T2 upon T1. This is the efficiency of the reversible heat engine. So from this we can write W upon T1 minus T2 is equals to Q1 upon T1, or we can also write this as Q2 upon T2 because it is a reversible heat engine. So here we can write Q2 as this K A T to the power 4 upon T2. So it becomes K A T to the power 3. So W upon T1 minus T2 is equals to K A T to the power 3. So from this particular equation we can calculate the value of A, and A is coming out to be W upon K T2 to the power 3 into T1 minus T2, or if we solve it further it becomes W upon K T1 T2 to the power 3 minus T2 to the power 4 if we take T2 to the power 3 inside. Then for a given value of W, whatever is the output of the engine, and the given value of T1, if you want to find out the value of A, what will be the value, minimum value of A, then we have to differentiate this dA by dt to, and we'll equate this to 0. So if we'll differentiate this particular equation and we'll equate to the 0, then it becomes minus W upon K into 3T1 T2 to the power 2 minus 4 T2 to the power 3 into T1 T2 to the power 3 minus T2 to the power 4 to the power minus 2 equals to 0. So if we solve this, either this should be equal to 0 or this should be equal to 0. If this is equals to 0, then T1 is equals to 2, T2. That is not possible. So T1 T2 to the power 3 equals to T2 to the power 4 is not possible. So that is not 0. So this must be 0. So if it is 0, then we can write this as 3T1 T2 to the power 2 is equals to 4T2 to the power 3. Or if we solve this one, then we get T2 upon T1 is equals to 0.75 or 3 by 4. So that is what is required to prove that the T2 by T1 should be 0.75 for the minimum area. So for minimum area, T2 by T1 is equals to 0.75. To find out the minimum value of area, we'll substitute T2 equals to 0.75 T1 in this equation as area will be equals to W upon K into T2. Instead of T2 we'll write 0.75 T1 to the power 3 into T1 minus 0.75 T1, as we are substituting T2 equals to this. So we get area minimum is equals to 256 watt W, 256 W upon 27 K T1 to the power 4. So that is the minimum area required. Now to find out this exact quantity for watt output as equals to 1 kilowatt as it is required, determine the maximum, that should be the minimum area of the panel for 1 kilowatt output. So here we will substitute W as 1 kilowatt, that is 1000 watt, and K is given as constant, is given as 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4, and T1 is given here as 1000 Kelvin. So if you substitute this and we'll find out the A minimum, then it is coming out to be 0.1672 meter square, what is required. So the minimum area required is 0.1672 meter square.